Hello, everybody. My name is Omer Reingold. I'm a professor of computer science at Stanford University. You can see behind me the Gates building at Stanford. And I'm really very happy to be part of this project with a lot of my friends and colleagues that mainly are other faculty members and researchers in the area of complexity theory, and more generally in the theory of computing. Um, so as I said, now I'm at Stanford University. I've been in various other institutes in the past. I studied my PhD at the Weizmann Institute in Israel, and I was a faculty member there. I've been to various research labs, like AT&T Research, Microsoft Research, Samsung Research. And for the last 5 or so years, I've been at Stanford. I study various areas in the theory of computer science, in particular complexity theory. One of the topics I study a lot is pseudo-randomness, studying objects that look random, although they have much less entropy than random, truly random objects. And I've also invested a lot of effort and a lot of thought into the societal impact of computation, which I think is a very, very important area for computer scientists to get into, because what we produce, our algorithms, um, have a lot of impact on individuals and societies, and have great potential of doing great things, but also uh, quite a bit of potential to do harm. And I think it is our responsibility. So I've studied privacy, and recently I'm studying, investing a lot of my effort in the field called algorithmic fairness. And in fact, in all of these areas, complexity theory, as well as algorithmic fairness, I think that my research uses one of the things that theoretical computer scientists do the best, which is the ability to model, the ability to abstract real problems at the right level of abstractions that allow you to say meaningful things and to understand them. And still, although these are simplified models, they are still very applicable to the questions you want to study. And kind of with that, we take more and more bites into the topic we want. And there's been lots of successes in areas like cryptography, uh, uh, algorithmic game theory, and others. And that's what I'm trying to do in algorithmic fairness, for example. But let's get to the topic at hand. So the first topic that we're going to discuss in this class, and that I will present to you, has to do with deterministic finite automata. This is a very simplified model of computation that essentially captures the idea of computation with constant amount of memory, with a fixed amount of memory. When we'll discuss more advanced models, this will be the main difference. More advanced models like Turing machines have more memory. We will define the kind of languages, the kind of computational problems that these finite automata can handle, and we'll call them regular languages. And we then try to characterize and also to understand, to study these regular languages, in particular through these very interesting notions of closure properties. We will consider two regular languages, two problems that DFAs can solve, and ask, can you combine them in some natural ways, and are the things you get after you combine them, are they regular languages as well? In the process of trying to prove these closure properties, we will encounter the notion of non-deterministic finite automata. This is going to be our first encounter with this notion of non-determinism, the idea that you're doing guesses that can be verified. This is a topic that would be very important in a later stage in our class, especially when we'll talk about the P versus NP problem. But we encounter it already here in a very simple setting. So it's a great opportunity to understand it already here. Then the next stage is to argue that non-determinism, although it looks very powerful, when you restrict it to finite automata, to constant amount of memory, non-determinism does not increase our powers. So the languages that non-deterministic finite automata recognize are exactly the same languages. These are the regular languages. Armed with this understanding, we can complete the proof of the closure properties. So regular languages have all these closure properties, which are very nice, but beyond that, what we will see next is that regular languages are characterized by closure properties. And we'll see it through this notion of regular expressions. And what we'll see is that these regular expressions, which are expressions that are defined exactly through these closure properties, are equivalent to DFAs and NFAs. They are yet another way of defining regular languages. And this is the picture that we're going to cover in the first topic, which in my opinion is a very nice picture that allows us to really have a nice understanding of what finite state machines can do. Hello everybody, and in this video we're going to introduce this notion of deterministic finite automata, which should be familiar to you from CS103. So this is kind of a review, and more than a single video will be kind of a review. You can, if you remember it well, you can spend little time with it. And let's look at what are these deterministic finite automata in the way that we are used to thinking about them, which is as this graph that we have. So what do these graphs represent? We have nodes that represent the different states the machine can be in. And these states come in two flavors. Well, more than two. We have the start state, which is a special state from which we start the computation. This is our first memory configuration. We have accept states. And accept states are denoted by two circles. And these are states that tell us when we accept a string. When we finish a computation in an accepting state, we know that we accept the string, the input that we got. The rest are just standard states. And in addition, we have the transition function that tells us how we move from one state to the other. So if we are in state Q0, we read a 1, we move to the state Q1. So for every state and for every alphabet symbol, we move to a different state. How do we compute in this kind of a graph, in this kind of a model? We read a string, a sequence of bits, in this case, or a sequence of alphabet characters. We read them from left to right, and for each one of them, we move based on the transition function. So we start in the start state, and then we read the first bit, which is a 0. The transition tells us to stay put. We stay in the same state. We read a 1, which moves us to the next state. We read another 1, get us to another state. And this one stays put. And since we ended the computation in an accept state, we are accepting this string. Right. And if we read the sequences and we got to a state that is not an accepting state, then we reject this string. So this is the computation, accepting or rejecting strings. Before we formalize this notion a bit better, let's ask, what's the motivation? Why are we spending so much time on this finite automata? And you also spend time in CS103. And since this may be your last theory class, I definitely don't want you to leave with the feeling that theory is all about something as simple or potentially uninteresting as finite automata. And so why do we need all these models all together? So we have here finite automata, we have a Turing machine here, we have the straight line and a compass that we discussed previously as a model of computation, we have Boolean circuits. There are so many different models of computations, and we're going to discuss several of them. But some of you know that Turing machines are very strong models of computation, and we think of them as being universal in some sense. So everything that can be computed by another model we think can be computed by a Turing machine. So why study these weaker notions like a DFA? And the reason is that different models can help us understand different aspects of computation. Specifically, DFAs will tell us what happens when the memory of your computation is very, very limited. So DFAs are characterized by being constant size memory. The memory doesn't grow with the length of the string. And it is accessing the input in a read-once manner. You go from left to right, you read every bit once, and that's it. And this is an example of the kind of things we'll be able to argue about later. We can ask, are these two aspects as important? Are DFAs change when you change one and not the other? Well, definitely if you add memory, then you get something that's stronger that we can show and we will show in the class. So constant size memory is important to being a DFA. But what about the read once input? So assume that instead of reading it once, you're allowed to kind of move back and forth on your input. Do you get something stronger? Can you compute things that you cannot with the DFA? And you will be able, and you will prove in one of your homework assignment that this doesn't add us any power. And this is a little bit surprising. So again, the question is are DFAs foundational and important and we should study them, or perhaps there are these archaic objects? Indeed, many classes like the one that we're teaching here are abandoning DFAs altogether. And one reason not to abandon is that DFAs are still important. There are things, because of their limited abilities, there are things that you can do better with the DFA. They're very important in various areas, like verification, for example. But since this is a theory class, this is not necessarily the reason for which I'm insisting on teaching DFAs. The reason is that it will allow us to talk about various aspects of computation in a very limited model for which we can say more things. So this is something that's so close to a Turing machine, and yet it is pretty far. We'll be able to introduce non-determinism, verified guessing, and it will be very weak in this sense. And similarly, we'll be able to show that you can optimize DFAs. You can compute the best DFA, the smallest DFA for any particular language. So these are things that you can do with the DFA that you cannot do with the general Turing machines. Through the notion of DFA, we'll be able to discuss all of these aspects, and it will be our first taste of what is computation. It will allow us to talk about non-determinism, learning, and it will allow us also to talk about limitations. There are not a lot of models in which you can show what cannot be computed in this model. And here we'll get very quickly into pretty strong statements about what can and cannot be computed by this model of computation. In addition, we are talking about it because of the relation to something that's really very interesting and practical and very realistic, which is streaming algorithms. This is kind of the modern incarnation of DFAs. And it will allow us also to talk about communication complexity. Again, something that's very interesting and very modern and important. So DFAs, perhaps not many of us that teach these classes actually study DFAs on a kind of regularly, but they're still, in my eyes, very useful to teach. This is a paper that introduced DFAs, and it won its authors the Turing Award. And the reason that is stated is because of introducing non-determinism. So similarly to the reason we are talking about it now, non-determinism was introduced in this context. Something more that's interesting to note when we kind of think about the computational lens that we discussed previously that one of the motivations that they discuss and is represented in this reference talks about the motivation in biology. So thinking about computation in other parts of science is not new. Perhaps it has been accelerated recently, but it is not new. It's there from the beginning. And so still in the level of motivation, streaming algorithms are computations that grow with the size of the input, but not too much. And they also process the input read once. So imagine a sensor that is giving us constant input. And this is something that's very relevant now in the Internet of Things world. We are surrounded by sensors that are creating more and more data, and we cannot store all this data to perform computation. We can just process it on the fly. So we get this sequence of bits, and the computation, the memory grows. And at some point when the sequence ends, the algorithm needs to output. This is something very relevant with the huge data that we are processing, and we'll get to it later in this chapter. So we need to dirty our hands and get a little bit into the definitions, into the notation. And as I said, this is one thing we get from talking about DFA is the opportunity to talk about all of this vocabulary. So what do we have here? We have the notion of an alphabet, which is just a finite set. You can think of the most common alphabet, which is the binary alphabet 0, 1, but sometimes we'll think of a larger alphabet, still a finite set. And then our inputs are going to be strings over sigma. So a finite length sequence of elements of sigma. And this is represented by a sigma star, the set of all strings over sigma. And I should add that this includes the empty string, the string that contains 0 elements from sigma. So 0 alphabet symbols. So this is all the strings of length 0 or larger over this alphabet. For a string x, we may want to talk about the length of it. We'll denote it by the absolute value of x. It's going to be the length of x. And the unique string of length 0 is denoted by epsilon, and is called the empty string. Now let's talk about languages. So a language over sigma is just a set of strings over sigma. So if you think about a language, of course, languages have, real-life languages have much more to them than just a collection of words. But for us, a language is just a collection of words, a collection of strings. So it is a subset of sigma star. And languages can also be viewed as Boolean functions over strings. This is just an equivalent representation. So the function that corresponds to a language L is the function f, such that f of x is 1 if and only if x is in L. Otherwise, it is 0. So this is just a relation between functions and subsets. So this is the indicator function of this language. And now we get to define DFAs more formally, and we'll define them as a 5-tuple. And some think that this is the difference between CS103 and this class, that now things are more formal, and now we have 5 tuples and later 7 tuples and all of that. That's not really what's important to us. The reason we're formalizing things is because we want to argue about them, but the actual formalization is pretty natural, and there is nothing particularly important about it. Still, let's do it. So these are the different ingredients that we need to specify in order to specify formally what is a DFA. Q is the set of states, which is finite, right? We have finite amount of memory. Q represents the set of states. Sigma is the alphabet, which is another set, again, finite. Delta, which is more interesting, is the transition function. This is the function that tells us, given the current state and the alphabet symbol we are reading now, to which state we are transitioning. Q0 is the start state. So it is one of the states, and it's a special one because this is the start state. That's where the computation starts. And F is the subset of accept states or final states. So these are the states that if we end with these states, we know that we are accepting. This is a very straightforward formalization of the picture we had before. With this formalization, we can ask what is the computation a particular DFA performs on a particular string. So let W1 up to Wn, each one of them is a symbol in sigma, be an input of this DFA. We say that M accepts W if there are n plus 1 states, R0, R1 up to Rn, with the following property. R0 is the start state, Rn is one of the accept states, and now we want to say that the computation takes us from R0 to Rn, meaning that delta applied to Ri and Wi plus 1 gets us to Ri plus 1 for every I between 0 and n minus 1. So given any one of these states, when we read the next symbol from W, from the word W, we reach the next state. Let's see it as an example. And this will be probably the last one, that definitely in the lectures and potentially beyond, we are going to have to specify the 5-tuple. So here is this DFA, and let's write it as this 5-tuple. So the states are just Q0, Q1, Q2, Q3. The alphabet here is 0, 1. The start state is Q0. The accept states are Q1 and Q2. And again, the most interesting part is the transition function, which is delta from Q times sigma to Q, and we'll specify it as a table. So given that you are in state, for example, Q0, and you read a 0, you stay put. In Q0, you read a 1, you move to Q1. So we can view it also in the picture. If you're in Q0, you read 0, you stay put. If you're in Q0 and you read 1, you move to Q1. So with this, we formally specified this DFA. You can see that especially the transition function is going to grow and be very large when the number of states is larger, and therefore we may not always choose to write down it as formally. So we have the definition of DFA. We know what strings the machine accepts or not. Now we can talk about L of M, which is the language of all the strings that M accepts. Sometimes we'll call it the language recognized by M. Sometimes it's the function that is computed by M. So this is just all the strings that the machine computes. So let's look at an example. We have this machine M. And now, what is the strings that are computed by this machine? And I'll ask you this several times in the video, and perhaps it makes sense to stop the video at each one of these times and trying to answer it by yourself. So what language is computed by this? Well, first, let's see the string 1010. You compute it. So this string is accepted. And the language is all the strings that begin with 1. Because you can see that you start in the start state. If you get with 1, you reach this state, which is kind of a sink. You can enter it, but you can never leave it. Everything you reach from now on will keep you here. And so everything that starts with 1 is going to be accepted. If you go with 0, you get to a non-accept state, which is again a sink, so you cannot escape it. It's a dead end. So you have two dead ends, and whenever you start with 1, you get to the accept dead end. When it's 0, it's the rejected end. So this is the language here. Here is another example. What is the language L of M here? So this is everything. You have a single state, which is an accept state. So everything is accepted. Or every string will end in the only state here. What is the language accepted here? Yes, this is the empty language, the language that contains no string. And here I want to emphasize something that I remember was very confusing to me, even when I took this similar class ages ago. The empty language is not the same as the empty string. In particular, the empty language doesn't include any string, and it doesn't include the empty string. And indeed, this DFA, even with the empty string will end in Q0, which is a reject state. Everything will end in Q0, which is a reject state. What is the language here? These are all the strings that have even number of ones. You can see that zeros don't change your state. Only ones change your state, and they change it from accept to reject. You start in accept, and every 2 ones you'll go back to accept. Let's try to prove it a bit more formally, not too formally. And how would you try to prove it? What is the technique that is natural to use here? Yes, induction. An induction on the length of the string. So we want to prove that the language is all the W's that have odd number of ones. It's very similar to the example from the previous slide. We'll prove it by induction of the length. The base case is when n equals 0. The only string of length 0 is the empty string, and this string is not in L, right? When you start in a reject state, and therefore you do not accept the empty string. And indeed, the empty string is also not in this language of odd number of ones. The empty string has 0 number of ones, which is not odd. The induction step is that suppose for all W's of length n, we assume that for all W of length n, M accept W if and only if W has an odd number of ones, And now we need to prove it for w's of length n+1. A string of length n+1 can be written either as w0 or w1, where w is the prefix of the string of length n. So if the last bit is 0, then you have w0. If the last bit is 1, then it's w1. And now we can continue with case analysis. If w has an odd number of ones, then a 0, then it means that it is accepted. It is in the language, which means that it is in the accept state. It reaches the accept state, and the 0 will keep it in the same place. On the other hand, a 1 will say that it no longer has an odd number of ones, and it will also move it to a reject state. So looking at the four cases, in the case analysis, we can show that a string of length n+1 is accepted if and only if it has an odd number of ones. Now let's look at a different task. Till now we were looking at particular DFAs, and we were asking what languages do they accept. Now let's try to build a DFA that accepts a particular language. Let's start with a simple language that contains a single string, 001. And here is a way to build it. You build it with 4 states. And these 4 states are trying to see the string 001. I'm going back. So now we want to build a DFA that accepts all the strings that contain 001 and doesn't accept strings that don't contain 001. We will build it using this DFA that has 4 states, and these 4 states are trying to look for the string 001. And once you see the entire string 001, you will be in a dead end, which is accept. So once you see 001, you will just continue there. The names of the states are very suggestive. Q is an arbitrary state. Q0 is a state which you reach after seeing 0 once. Q00 means that now you've seen 00 are the last 2 bits that you saw. And 001 means that you saw 001 recently or before. And the construction is pretty natural. So when you're at Q, meaning that you didn't see 0, the last one is not 0, and as long as you see 1, you stay put. If you see a 0, you move to Q0 because you just saw 0. From Q0, if you see 1, you go back to Q because the last one was 1. On the other hand, if you see 0, then it means that you can move to Q00 because you just saw 0. And as long as you keep on seeing 0, you can stay put because it means that the last 2 bits were zeros. So you saw Q00. Now, if you see a 1, you're going to move forward to Q001 because you just saw the string 001, and you're going to stay put because this means that you've seen the string 001. So with all of the vocabulary that we developed, we can now define a language L prime to be regular if it is recognized by some DFA. That is, there is some DFA M such that L prime is L of M, the language recognized by M. We by now know some examples of regular languages. So L prime, which is all the strings that contain 001, is regular. We just built a DFA to recognize it. and L prime, which is all W's that have even number of ones or odd number of ones. And these languages are regular as well. So these are the examples we have so far of regular languages. And we are going to see much more about these regular languages in the next video. Hello, everybody. So last time we defined deterministic finite automata, DFA, and we talked about languages that a DFA recognize. And these languages that are recognized by some DFA are called regular languages. And now we want to understand the properties of regular languages. We'll talk about some interesting closure properties of regular languages, and they will turn out to be very interesting in the sense that they are not only properties of regular languages, but they are actually going to define regular languages. So here are the properties we are going to discuss. Assume that you have two languages, A and B. We can define the union of these languages, or strings that are either in A or in B. So just the union of A and B is subsets, right? We said that languages are subsets of words, and we are just talking about the unions. Similarly, the intersection is strings that are both in words that are both in A and in B. The complement of a language is the set complement of the language. All the words such that they are not in A. We can talk about the reverse of a language, which is just the reverse of every word in the language. So W1 up to WK is in the reverse of A if WK to W1 is in A. Concatenation, A concatenated with B, just says that it's a concatenation of words VW, where V is in A and W is in B. And the clean star, so A star is the concatenation of S1 up to Sk, where K is larger or equal to 0, where every Si is in A. So now that we can talk about concatenation of 0 strings, so A star always includes the empty string. The empty string is in A star for every A. Otherwise, it's words that can be split into the concatenation of words from A. And the theorem is that if A and B are regular languages, so are A union B, A intersection B, the negation of A reversed, A concatenated with B, and A star. So this is the theorem, and we'll start working our way through proving it. We won't get all the way, we'll get stuck at some point, but this will help us introduce the notion of non-deterministic finite automata. So let's start with the union theorem for regular languages. Given two languages, L1 and L2, the union of L1 and L2 is just the set union of these two languages, so words that are either in L1 or in L2. And the question is how to prove the union theorem. The theorem is that the union of any two regular languages is also regular. And to prove it, this will denote our proof. We'll recall that L1 and L2 are regular. We need to take advantage of this property. This is essentially the only thing we know about L1 and L2. And the fact that they are regular means that there are finite automata M1 and M2, such that L1 is the language that M1 accepts, recognizes, and L2 is the language that M2 recognizes. And now what do we need to show? We need to show that there is another finite automata M that will recognize the union of L1 and L2. So that's essentially what the theorem says. We didn't do much but parse the meaning of this theorem. So the idea is to construct M that in parallel runs M1 and M2 and accepts if one of them is accepting. So we will run the machine for L1, the machine for L2, and if one of them accepts, so will we. So these are the machines as before. And to run in parallel, in order to run in parallel, we'll define the set of states of M to be pairs of states, where Q1 and Q2, where Q1 is a state in M1 and Q2 is a state in M2. So Q1 belongs to Q1, to the set Q1, and Q2 belongs to the set Q2. So when we're saying that in parallel we're going to run M1 and M2, M1 is going to run on the first component of the state, and M2 is going to be run on the second component of the state. The start state is Q01 and Q02, right? Because we want these to be two parallel runs, and both of them needs to start from the corresponding start states. The accept states are going to be Q1, Q2, where either Q1 is an accept state or Q2 is an accept state. And the transition function is exactly the one that allows us to say that we are running in parallel. So delta that gets the state Q1, Q2, and the symbol sigma will move to the state which its first component is delta 1 of Q1 and sigma, whatever M1 does when it is in Q1 and reads sigma. And the second component is delta 2 of Q2 and sigma. So let's see this transformation on this very, very simple example. So we have M1 and above and M2 below, and now we want to create M. So M will have states that are pairs of states. So Q0, Q1, and P0 and P1. So these are the states: Q0, P0, Q1, P1, Q0, P1, Q1, P1. And these are the transitions. And you can verify that indeed each one of the transitions correspond to running in parallel M1 and M2. So this says that the union of two regular languages is regular. Now we want to somehow argue that the intersection of two regular languages is regular. How will we do that? That's almost the same proof. We just need to change our notion of accepting states. So instead of accepting state being ones where either the first state is accepting in M1 or the second component is accepting in M2, we want both of them to be accepting. So in this example, we need to turn this state and this state to be reject states, whereas the only accept state is Q0 and P1 because Q0 is the accept state in the first automata and P1 is the accept state in the second automata. So this is going to be the only accept state. So in the more formal description, the only difference is that is in the accept states. Instead of asking for Q1 to be in F1 or Q2 is in F2, here we'll ask for Q1 to be in F1 and Q2 in F2. This is, we've proved almost simultaneously. We recycled the proof of the union theorem to be a proof of an intersection theorem. So the union And so it's closed under union and it's closed under intersection. What about the complement theorem for regular languages? So this is the third closure property. The complement of a regular language is also a regular language. So if L is regular, then we want to say that not L is also regular. And how will we do that? Well, we'll take the automata that accepts M and we're going to revise it to be an automata that accepts not L. What would be that automata? Well, yes, we're going to change every accept state to reject state and reject state to accept state. This kind of shows us the computation that is always correct is essentially the same as a computation that is always wrong. And we'll discuss it later in the class as well. Right, so that's the proof. The proof is just switching the accept and reject states. So we did 3 out of 6. We should feel very happy with ourselves. And now kind of let's try to do the 4th one. And this 4th one will give us a little bit more trouble. So the 4th one is the reverse theorem. The reverse of the language L is all the words such that when you reverse the word, you get a word that is accepted in L. And the theorem is that if L is regular, then L reverse is also regular. Meaning that if L is recognized by the usual kind of DFA, then L reverse is recognized by a DFA. And essentially it means that you can recognize L, you can take every right to left computation and replace it by left to right computation. So this is essentially what the reverse means. The reverse means that instead of looking at the string W1 up to WK and asking if it is in L, we're going to read it from the other direction and ask it whether it is in L. So how are we going to reverse DFA? The idea is that as we assume that L is a regular language, let M be the DFA that recognizes L. And we want to build a machine MR that accepts LR. And we're just going to try to reverse M. So if M accepts W, then W is describes a directed path in M from the start state to an accept state. Let's reverse this path and ask for a path from the accept state to the reverse state. So try to define MR as M with the arrows being reversed and turning the start state into final state and final states into the start state. The problem is that this is a great kind of idea, but it doesn't give us a DFA. When we reverse a DFA, we don't get exactly a DFA. MR can have many start states. Some of the states may have more than one outgoing edge, and others will have no outgoing edge. And also we may have more than a single start state. Wait. Let's not be harsh. We don't need to throw out this idea. In fact, this idea will give us something very, very useful. And so let's entertain this idea a little bit further. So recall this is the DFA that recognizes the language that of all the words that contain 001. And let's try to reverse it. We're reversing the edges. and we're reversing the start and end state. In this case, there are only one, so one problem is solved here. But now the question is what happens when we compute on the string 1, 0, 0. So we can do various things. We can take 1, 0, 0 and get to accept. And this is an outcome that we actually want to have because 0, 0, 1 is accepted by the original DFA. But what happens if instead of doing that, we just take 0, stay put, sorry, take 1, stay put, and now when we read 0 and 0, we need to continue staying put. So because this state has two edges marked 1, we can do one of two things. One of them can lead us to accept, but the other one leads us to reject. So we need to define the notion of accepting a little bit different, and we will say that the new machine accepts a string if there is some path that reaches some accept state from some start state. So it's true that some ways of doing the computation, like here, when you start with 1, stay put, and then you stay put with 0 and 0, will actually make you reject. But as long as there is one path that is accepting, then we say that this new machine that is not exactly a DFA accepts. And now we are ready to name this machine. We'll call it non-deterministic finite automata, NFA. And we are ready to analyze it. And so this thing that is a byproduct of trying to prove a particular theorem will turn out to be extremely interesting.